Okay, we're gonna do rational functions. Rational functions are functions that can be written as a polynomial. So a polynomial 1, let's call it, of x over another polynomial, let's say polynomial 2 of x. So those are rational functions. We had a video before about polynomials, so now we are doing polynomials divided by polynomials, and that's what a rational function is. Keep in mind that the number 1 is a polynomial. So if you have a polynomial over 1, any polynomial, p of x, divided by 1, which is, again, p of x, and I'm not stating that this is equal to that, this is a different example. Um, 1 is a polynomial, and consequently, a polynomial over 1 is a rational function. This is what I'm trying to say. Okay, we got linear functions. You know linear functions such as y equals mx plus b. So those are straight lines. Let's pretend this is the set of linear functions. So linear, okay? And then we got quadratic functions. Quadratic functions are gonna be here. You know, you got quadratic, you know, the parabolas, and then you got cubic and all that. So all the polynomial functions are gonna be here. Those are polynomial functions, polynomial. Well, inside of the rational functions, we have the polynomial functions. So these are, all the polynomial functions are gonna be part of a bigger set, which is gonna be the rational functions. So it is, what we are doing is similar to what we did with numbers. We started with natural numbers, then we had the integers, and then we went to the rational numbers and the real numbers and so forth. So that's kind of what's going on here. We got linear, quadratic, cubic, fourth degree polynomials, and then, you know, all of those are all the polynomials. Inside of the polynomials, we have, rather, inside of the rational functions, we got all of the polynomials. So polynomials will be rational functions. Why? Because they can be written as a polynomial divided by 1, and 1 is a polynomial. Just the number 1 is a polynomial. Yeah. However, we're going to be more interested in looking at functions that are here that are not polynomials. Yeah. So again, we want to be interested in functions that are rational functions, which at the same time are not polynomials, because they're more interesting in the sense that that's the new thing that we are learning. So just be aware that polynomials happen to be rational functions. I can see myself asking that question in a multiple choice problem. Are polynomials rational functions or not? And simple yes or no. Yep. And the answer, of course, is yes, polynomials are rational functions. But it is more interesting to see polynomials that are, rather, rational functions that are not polynomials. Such a simple example, let's write this as an example, is f of x equals 1 over x. This is one of the simplest true rational functions, in the sense that it is not a polynomial at all. One important thing that this function has is that now we have asymptotes. Another important thing is that the domain is not all the real numbers. We cannot plug in 0 for x because it is prohibited to divide by 0. So 0 is not included as part of this domain, or the domain of this function. So we cannot have 0. There's tons of things that we are doing with this. So in this video, what we are going to do is analyze rational functions. So we're going to perform an analysis of rational functions. Yeah, and there are many angles, many things that we need to observe about rational functions. The first thing that comes to my mind is symmetry. Okay, notice that f of negative x will be 1 over negative x. And then we can move the negative out. So this is negative 1 over x. And then let's keep it there. While negative f of x is, if you start out with this function, just put a negative in front. And notice that those two are the same. We did this in previous videos. So this is a little bit of a review. If those two are the same, that means that the function is odd. Same. So f is an odd function, which means that it is symmetric with respect to the origin, across the origin. Okay. We also want to look at some values, some inputs and outputs. Let's start with an easy input, the input of 1. So 1 over 1 is 1. If we put 10, okay, then 1 over 10 is 0.1, 0.1. If we put 100, so we are going far away fairly quickly. 1 over 100 is 100th, and 100th is the same thing as 0.01, 0.01. And then if we put 1,000 in the input, then we're going to have 0.001. And that gets very, very small. It's very, 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 very tiny. And 1,000 is far away. But so when we look at the output, so 1, 1 is one of the points on the graph. But then when we go 10, see, I'm going to make a sketch, which means the scale is not going to be correct. Even within one axis, I'm going to change the scale within the axis in favor of looking at information as good as we can. So again, this is going down quite quickly, you know, from 1 to 0.1, 1/10. And then, well, see here, I'm changing the scale. This is, I'm assuming this is 1. And then we go down to 1/10. So this would be 10, which doesn't make sense, because if this is 1 and this is 9, you know, from 1 to 10, there's 9 units. That doesn't make sense. But I'm making it squeeze, and I'm squeezing the picture in here, because I'm not going to draw 1,000 of those units. That would be too far out. That would be way, way. Which way am I facing? It will be like in East Grand Rapids or somewhere. I'm in downtown right now, so, and that way is east. Yeah. Anyway, so if we keep going down, or if we do 100 here, which again, I understand that doesn't make sense because of the scale, but we're changing the scale on purpose. So then we go down even farther, and even if we have 1,000,000 here, so 1,000,000, then we would end up with 0.1234 and then 1. So that's really, really tiny. And that's the idea of an asymptote, that we're getting closer and closer, and yet we are not really on it ever. So this line here is an asymptote. The graph keeps going closer and closer to that line. And then going the other way is also true. If you have 0.1 as the input, the output is going to be 10. 0.01 in the input gives us 100 on the output. 0.001 gives us 1,000 on the output. So if we divide by a tiny number, we end up with a bigger number. The tinier the number, the bigger the output. And so I'm going to draw a new picture. So this is the shape that we have, this curve. And then we have this asymptote. So this vertical line, which is not really part of the graph, but we'd still draw it as a dotted line, is the vertical asymptote. The vertical asymptote will be x equals 0. The horizontal asymptote is y equals 0. And we put arrows indicating we're getting closer to those asymptotes. The function is odd. We established that earlier in this example, which means that the graph has its own projection over the origin. So the graph looks like this. We know that the domain cannot include 0. So let me continue with this analysis, the analysis of this function. The domain goes from -infinity to 0, union 0 to infinity. So we're excluding 0. And then after looking at the picture and after doing this table and realizing that we have a horizontal asymptote here, we realize that the range is also all the numbers except 0. So the range goes from -infinity to 0, union from 0 to infinity. That's the range. Symmetry, there is no x-intercepts or y-intercepts. We don't cross the x-intercept or the y-intercept at all. I'm trying to think what other piece of information we need to include in this analysis. I just misplaced a page. Yep, I found it. So domain, vertical asymptote, horizontal asymptote, symmetry, x-intercept, y-intercept, and the sketch. Yeah, we kind of have a pretty good analysis of this. So the idea behind rational functions will be this video to look at functions that are rational and analyze them, trying to find out whether they're symmetric, their domain, the range. The sketch is very important. That's one of the most important things we want to do with rational functions. And we just want to get to know rational functions really well. So we find information about them. Before we continue, let's analyze one rational function that brings up an important point, an idea here. Consider two examples. Y equals x plus 1. You are familiar with this. I meant y. Yeah, there you go. Y equals x plus 1. That's a straight line going through 1 at a 45-degree angle. Slope is 1. Y-intercept is 0, 1. And so there we have it. Compare that with versus b. Y equals x plus 1 times x minus 2 over x minus 2. Those two are not the same function. They're not the same. They're not going to produce exactly the same graph. And we want to make sure we get this out of the way right away. Because taking this as is, we cannot have x equal 2. So because the x minus 2 is in the denominator, we absolutely cannot have x equal 2. Because we may never, ever, ever divide by 0. We cannot divide by 0. And we may be thinking, wait a minute, but those two factors cancel out. They cancel out if we allowed x to be different than 2. But if x is 2, then we cannot cancel it out. In other words, when we cross those off, we still have this restriction in the function. This restriction is not going to go away because we crossed that off. If it goes away, that means we did not do this correctly. In other words, if we say that is equal to x plus 1 because we crossed those off, it is true as long as we keep this restriction here as well. As a graph, this is what's going on. So the graph of this function will be almost the same as that, except there is going to be a hole. So pretend that is the same line with a hole in it. My picture didn't look very good. I'm going to draw a new picture on the next page. Yeah. So sometimes this is what I do. I draw the picture, and then I draw a hole. So pretend there's a hole there, and the hole will be in the place where if we were to put 2 here, we would have an output. So the whole happens to be at 2 comma 3, because if you put 2 in here, we're not supposed to, because 2 is not in the domain, but if we were able to, we will have 2 plus 1, 3, so the whole is at 2, 3. We have the same graph as A, except that this one doesn't have a hole, this one does have a hole. And we exaggerate the hole. We make a big deal about it because we want to point out how those two graphs are different. If you put this on a graphing calculator, maybe the hole will show up or maybe not. It depends on where the pixels are placed, how the pixels are connecting the line together. So it may or may not, but we know there is a hole in there, and that's why we want to analyze those kind of functions. So be aware, anytime we have a factor that cancels off with another factor, a hole will show up every time, unless we have a function that, rather, a factor that is never equal to 0. Yeah, let's do an example. Example 3. There are expressions that are never 0. So for instance, example 3, let's say you have f of x equaling 1 over x squared plus 1. Okay, we are aware that x squared is always positive or 0. If you plug any number for x, we're going to end up with a positive number. The least we will have is 0. If we, on top of that, add 1, then we will have a quantity that is always positive. Always, always positive. So the denominator will never be 0, which means that the domain is all the real numbers. So the domain goes from negative infinity to infinity. There is no hole, there's no vertical asymptote, nothing. So there's a lot of things we have to remember in this video. A lot of things, such as x squared plus 1, not to be confused with x squared minus 1. Yep. So the graph of this is a Bell function. It is not the statistics Bell function. That's a different function. But it's kind of like it. We do have a horizontal asymptote, not a vertical asymptote, but yes, a horizontal asymptote. Y equals 0, horizontal asymptote. So that means that on both sides, the graph keeps going closer and closer towards 0 without touching it. The highest point will be 0, 1, and it curves this way smoothly. And there we have it. That's a sketch of the graph of this function. Again, it doesn't have any holes and it doesn't have any vertical asymptotes. Not to be confused with example 4. Actually, I'm going to write it on the next page because I'm running out of space. So example 4, if f of x was 1 over x squared minus 1, notice that is a big difference. X squared plus 1, that is very easy to confuse. If you have x squared plus 1 versus x squared minus 1, pay close attention. This one has 2 vertical asymptotes because we can rewrite this as x minus 1 times x plus 1 in the denominator. And that means that we may not have 1 or negative 1 as part of the domain. And we got to do this little by little. I'm kind of showing you a lot of information all at once, but we're going to slow down a little bit in a little bit, perhaps after this example, and show how we actually get all of the pieces of information. So right now I'm just showing you the difference between this function and this function, and I'm going to show you what the function looks like. But then we're going to come back and realize where all that information came from. So this graph is going to have 3 branches. We have 2 vertical asymptotes, one at 1, the other one at -1. And then we have a branch going this way. This graph happens to be symmetric over the y-axis. So we have this. Yep. And then in the middle, we have sort of like a U upside down kind of graph here. And then the maximum will be at, when we plug in 0, we have 1 over 0 minus 1. So that's 1 over -1. So here, this maximum will be at 0, -1. That's a local maximum. Of course, it is not the maximum of the entire function. We have a horizontal asymptote of y equals 0. Again, I'm perhaps overwhelming you with a lot of information, but we have to be able, within this video, be able to come up with all of this all at once. Boy, there's a lot of information that is going on here. How do we get all of this at one? Well, let's start from the beginning. Let's start with vertical asymptotes. So let's start talking about asymptotes. Asymptotes. Okay, so the asymptotes occur when the denominator is 0 and the numerator is not 0. Oh, actually there's two. There's vertical, actually there's more than that. Vertical asymptotes, horizontal asymptotes, and slant asymptotes. So let's talk about vertical asymptotes. Vertical asymptotes occur when denominator is 0 and numerator is not 0. It's not erasing. I'll tell you this. Oh, but now it's not erasing still because I have to get to the point where there. Okay, sorry to be wasting your time with erasing. Anyway, 0. And numerator is not 0. Okay, so that's when the vertical asymptotes happen. Back in this example, if x equals 1, this becomes 0, which causes the whole thing to be 0, because if x is 1, then we have 2 times 0, 0, but the numerator stays as not 0, so that's why we have a vertical asymptote there. So we search for the vertical asymptotes, there is 1. Another vertical asymptote will happen when x is -1, because -1 plus 1 is 0, and -1 minus 1 is -2. 0 times -2 is 0. The whole denominator becomes 0, but the numerator becomes 1. It is just 1, so it is not 0. So that's when we have a vertical asymptote at x equals -1. Now, going back to example 2, where's example 2? The one with a hole in it. I guess I'm missing a page somewhere. Anyway, let me write it here. Example 2, it had x plus 1 times x minus 2 over x minus 2. Now, the problem here is that 2 causes the denominator to be 0, but also 2 causes the numerator to be 0. If a number causes both the numerator and denominator to be 0, we have a hole. We don't have necessarily a vertical asymptote, although it actually gets more complicated than that. Yeah, I believe it does get more complicated than that. Yeah, we have to address that. But in general speaking, if we have the same number of factors, an x minus 2, a single x minus 2, and a single x minus 2, one in the numerator and one in the denominator, then we have a hole. Yep. So Remember, vertical asymptotes come from when the denominator becomes 0. Okay. That was example. Well, let's talk about horizontal asymptotes. Okay. Horizontal asymptotes occur invariably when the degree of the denominator is larger than the degree of the numerator. Okay. So actually, that's partially correct. There's more to that. Okay. So there's two kinds of horizontal asymptotes. Y equals 0 will be a horizontal asymptote if degree of denominator is larger than degree of numerator. Invariably, that's always going to happen. So in example 4, the degree of the denominator is 2. The degree of the numerator is 0. No, 0 degree. 2 is larger than 0, and that's why we have a horizontal asymptote y equals 0. Yeah. Yeah. And the reason is because these numbers are going to get larger, very, very large eventually. You know, if you plug in 100, you're going to end up with 99. No, I'm sorry. If you plug in 10 for x, which is not that far out, we're going to end up with a denominator of 99 because 10 squared is 100 minus 1 is 99. 1 over 99 is going to be very tiny out here. Yeah. And so that's why we have a horizontal asymptote. And the larger the x, the even larger, if that would be a word, would the denominator be. So if x is 100, then we have 10,000. When we square that minus 1, that is 9,999. And 1 over 9,999 is going to be very, very tiny, which indicates that we're getting closer and closer to 0 without ever getting on 0. So if the denominator's degree is larger, then we have y equals 0 as a horizontal asymptote. If the degree of the denominator is equal to the degree of the numerator, then we have that the horizontal asymptote is a constant. So we end up with y equals a constant. I'm going to use k for a constant, okay? If, and k not equal to 0, by the way, I should probably state that, k not equal to 0, if degree of denominator is equal to degree of numerator. Okay. Let me give you an example. Let's say example 5, y equals 3x squared minus 7x plus 9 over 4x squared plus 8x minus 17. So the degree of this polynomial is 2. The degree of this polynomial is 2. They have the same degree. So this function has a horizontal asymptote, HA for short, horizontal asymptote, and it will be y equals, and what we have to do is simply divide the coefficients of the polynomials, the leading coefficients, which means the first coefficients or the coefficients of the highest degree in the polynomial, which are 3 and 4. All you have to do is put down 3 over 4, and that's it. That is the horizontal asymptote of this polynomial. Yeah, we're going to do some examples about that, but I just want to focus or emphasize how the horizontal asymptote is found. If we have the same degree, then divide the coefficients. And again, we're going to do examples like that. And then we have slant asymptotes or oblique asymptotes. Okay. And it shouldn't take us too much to figure out when that happens. We said there are, well, horizontal asymptotes y equals 0 if the degree of the denominator is larger than the degree of the numerator. If the degrees are equal, we also have horizontal asymptotes, but not y equals 0, y equals a constant. And we just went over how the constant is found. But what is the case we're missing? So the degree of the denominator is larger than the degree of the numerator. The two degrees are equal. And the case we're missing is when the degree of the numerator is larger than the degree of the denominator. So there are three cases. Sometimes I tell this is bottom heavy in the sense that the bottom is larger than the top. This is even, the top and the bottom are the same size. And then the other case is when the top is heavy. So we have this scenario, slant or oblique asymptote, if degree of numerator is larger by 1 than degree of denominator. Yeah, I just realized if we want to have a straight line, the degree has to be larger by 1. If the degree is larger by 2, then we don't have an asymptote as a straight line. We have some kind of asymptotic behavior, but let's not get into that. Let's just assume that the top is larger by 1. Yeah. So there are some cases that we could consider yet, which we're not going to consider here. So, yep. Some of the pages I was looking at fell off, so. Okay. And there's one other thing that I like to include, which may not be in some books, and that is what I call the chart of signs. It is in some books, and it isn't in some other books. So, chart of signs. Yeah. And that chart of signs will be, a line in general, the number line, and then we're going to have points that we have to where we may have a vertical asymptote, so we can denote them like so, and then we have points where we would have x-intercepts. And if we have factors that contribute to those points, then we can draw whether the function is positive or negative across this number line. Typically, we start with positive here. So I'm going to label this as a number 1. If there is no extra negatives, and I'll show you what I mean by this in a moment, but we start with positive, and then we go, every time we cross one of these points, I'm differentiating the points. Those are the vertical asymptotes, and this is an x-intercept. But if we have single factors contributing to those points, then we simply alternate. So we go from plus to minus to plus, back to minus. I really have to do an example to show you what I mean with all of this, because it can get, just showing one area of this doesn't tell us the whole picture. It's it's like taking a picture of somebody and then just, I don't know, a little area of the palm of your hand. You know, if you just focus too much on one little area, then that doesn't tell us much about the person um, at all. But maybe if you take a big picture, you know, a picture of the person, you know, from head to toes, then you can tell what the person looks like. But if you take a picture of the person from a plane, when the plane is flying, then you won't be able to see the person either. So it's got to be just the right distance. And what I mean by that is showing you each specific thing one by one in the abstract is difficult to grasp until we have a function to work on. So let's do a bunch of examples. I'm just looking what example number is next. So 6, example 6. I'm going to start with a new page. Okay, 6. All right. So let's say we have a function that has one factor on the numerator, x minus 1, two factors in the denominator, x minus 2, x minus 3, and that's it. Let's start with that. See, there are many, many variations and of this kind of example, even with just those 3 factors. But we want to analyze it. Okay, so typically I'm going to give you problems where the denominator and numerator are already factored. If they're not factored, then we have to factor them. So we have vertical asymptotes coming from 2 and 3 because they cause the denominator to be 0, and yet when you plug in 2 or 3 on the numerator, you don't have 0. So we have vertical asymptotes. Vertical asymptotes are x equals 2, comma, and x equals 3. We got 2 of them. That also tells us the domain, by the way. I'm not going to focus on the domain yet. Do we have a horizontal asymptote? Well, the denominator has degree 2 because there are 2 x's that will multiply. If we multiply this out, we end up with x squared minus 5x plus 6. So we have a quadratic, a polynomial of degree 2. There are 2 x's that are going to multiply, and we're going to end up with x squared. The numerator is a polynomial of degree 1. The denominator is bigger, so this function is what I would call bottom heavy. If we have a function that is bottom heavy, that means that the horizontal asymptote is y equals 0. So horizontal asymptote is y equals 0. Not all functions have a horizontal asymptote. Some of them have a slant asymptote. Some functions don't have a horizontal asymptote or slant asymptote. So we have to be aware of all the possible different things that a function may or may not have. We always ask, and if something does not apply, then we just say it doesn't have it. Yeah. So we expect in quizzes and tests to be asked whether a function or what is the horizontal asymptote of a function. And if it doesn't have one, then just say so. This function doesn't have a horizontal asymptote. We always ask it though. We typically do, because that is just like filling out a form when you go to a doctor's office, you know. I go to the doctor's office and then, you know, they ask me to fill out this form. And one of the questions is, are you pregnant? Well, it does not really apply. They shouldn't even ask me that question because it doesn't apply to me, but it is still in the questionnaire. So I have to fill it out. What else? Where was I going with this? So we got the vertical asymptote. Oh, do we have any symmetry? I don't think so, because the horizontal asymptote, the vertical asymptotes rather, are on the right of the y-axis. You know, 2 and 3. Had there been any kind of symmetry, we would have a mirror image across the y-axis. We would have -2 and -3 as vertical asymptotes. So no, there is no symmetry at all. Let's see what else we can go for. the chart of signs, okay, that I was trying to explain in the previous page. So we got 2 and 3 as vertical asymptotes, vertical asymptote. And then, oh, when is this equal to 0? We want to also figure out x-intercepts. So this is equal to 0 when the numerator is equal to 0 and the denominator is not equal to 0. And when is this equal to 0? When x equals 1. So here we have a x-intercept. Now, if you plug in a big number, and by big in this context, I mean bigger than 3, say 5, you end up with 5 minus 1, 4, 5 minus 2, 3, and 5 minus 3, 2. All the numbers end up being positive, and consequently, the output of this function is positive past the 3. So we have positive. Again, how do I find that? I just picked a number at random past the 3. 5 seems like an easy number. And if I find f of 5, we get 4 divided by 3 times 2, 6, which is 2/3. But what the important thing about this number is that we have a positive output. So the output is always going to be positive past the 3. And the reason is because the function will be continuous past the 3. If the function was ever negative, because of continuity, we would have to cross the x-axis, which means we would have to have an x-intercept, but the only x-intercept is over here on the left. So we don't have anything there. Between 2 and 3, now we could plug in a number between 2 and 3, say 2.5. But since we have single factors, the sign is going to change from positive to negative, from negative to positive, from positive to negative here. Yep. Okay. So if we have single factors, a single x minus 1, a single x minus 2, and a single x minus 3, the signs will alternate. If you're in doubt, you can always plug in a number, such as 2.5 in here, and then figure out whether the number is positive or negative. The number, if you plug in 2.5, we're going to end up with a negative number. And that's why the sign between 2 and 3 is negative. The sign between 1 and 2 is positive. If you plug in a number between 1 and 2, say 0.5 into this function, 0.5 minus 1, 0.5 minus 2, 0.5 minus 3, we're going to end up with a positive number. Is that so? Oh, I meant 1.5, not 0.5. Yeah, this is 1. If we put 1.5 here, 1.5 there, 1.5 there, we're going to end up with a positive number, because 1.5 minus 1 is going to be a positive number. 1.5 minus 2 is a negative number. 1.5 minus 3 is a negative number. Two negative numbers multiplied together give us a positive number. This is positive to start with, so the whole thing is positive. Okay, so that's that. And now we are pretty much ready to draw the picture. Okay, so, well, we still have to figure out the y-intercept, but I usually do that last. Okay, so we got vertical asymptotes at 3 and 2. So I draw vertical asymptotes at x equals 2, x equals 3. We have a horizontal asymptote of 0. And we have an x-intercept of 1. Okay, so there's going to be branches. The graph is going to be positive here, and the only way you can have a positive function with this vertical asymptote and that horizontal asymptote is by doing this. Between those two asymptotes, the graph is going to be negative. And the only way to have a negative branch, each one of these are called branches. The only way to have a negative branch is this way between those two asymptotes. It's kind of like a U upside down. On the left of this asymptote, well, the function is positive, but then it is zero because we have a zero, an x-intercept, and then we have to get close to this horizontal asymptote, so we're going to do this. I know it is confusing, but we have to really practice. There's a lot of parts to this, and that's what I think makes it confusing. But if you practice, it shouldn't, eventually it shouldn't be too bad. Oh, let's make sure we know where the y-intercept is. If we plug in 0, we can do that here. F of 0 will be 0 minus 1 over 0 minus 2 and 0 minus 3. And that's going to be negative 1 over negative 2 times negative 3. And that's going to be negative 1 over 6. So this point here will be 0, negative 1 over 6. Yep. And then we have to label the horizontal asymptote. We label the vertical asymptotes. There's a maximum here. What is it? We don't know. Don't assume that it is necessarily right in the middle, 2.5. We don't know what it is. We kind of need calculus to really find this point. Okay, let's move the factors around. Let's say example 7. F of x equals x minus 2 on the numerator, x minus 1, and x minus 3 in the denominator. So I'm using the same factors, x minus 1, x minus 2, and x minus 3. But instead of having x minus 1 on the numerator, now we have x minus 2 on the numerator, and x minus 1 is in the denominator. What difference does it make on the graph? And I know this is a lot to do in one video, but this is the way it is. It is rather complicated of a topic for one video. But at the same time, we don't want to overdwell on it. We don't want to spend way too much time on it. We want to have a good grasp of what we're doing without spending way too much time on this. So denominator is big compared to the top. So this is bottom heavy. So horizontal asymptote, y equals 0. Vertical asymptotes, 1 and 3. So vertical asymptotes, x equals 1 and x equals 3. I'm going to do a quick chart of signs. Okay, so we're going to have 1 and 3. And in the middle, we're going to have the x-intercept. The x-intercept is when the numerator is 0 and the denominator is not 0. All of the x's are positive. That means that if you plug in a big number such as 10, that's going to be 8, 9, 7. All the numbers involved are going to be positive, and so the result here is going to be positive. As we go across each one of those factors, we're going to alternate signs. Start with positive, negative, positive on the right, negative, then positive, then negative. Okay. We pretty much have all the information we want to start sketching this graph. So everything is to the right of the 1. Let's draw the horizontal asymptote first, y equals 0. Then we have a vertical asymptote at 1, x equals 1, another vertical asymptote at 3. And we have an x-intercept here. The graph is positive on the right of the 3. The only way it can be positive is this way. So if you got a horizontal asymptote, vertical asymptote, and no x-intercept, that means that this is the only way we can go. Then we have negative, positive, negative. So we have a negative graph here. And the only way it can go is this way. Between 1 and 3, we go from positive to negative. The only way we can go positive is this way, connect with the x-intercept, and then we gotta go negative, positive, negative. So this is getting closer to the asymptote, and this is getting closer to the vertical asymptote. And that's pretty much it. Other than figuring out the y-intercept, which is gonna be here somewhere. So I did not draw the y-axis on purpose. I don't wanna draw attention to the y-axis. I wanna draw more attention to the vertical asymptotes. Keep in mind that the y-axis will be here at 0. And then we have to figure out the other component. When x is 0, let's figure this out down here. F of 0 will be 0 minus 2 over 0 minus 1 times 0 minus 3. And that's going to give us negative 2 over negative 1 times negative 3, positive 3. So we end up with negative 2/3 for the y-intercept. Again, I'm not drawing the y-intercept, but there's the y-intercept. The x-intercept will be 2, 0. I want to make sure I did draw that on the previous page. I did not label it. We should label it. So the x-intercept is 1, whoops. 1, 0. 1, 0. Rather, the x-intercept, there's the y-intercept. Okay. Example 8. I know you're thinking, man, I'm not getting this. We don't want to, we want to use only basic information. We don't want to have too much information about this. So try to use as little information as you need to understand it. In other words, if this is vertical and horizontal and the function is positive, there's only one way to get to those two asymptotes. And same thing here. The only information I'm using is this is an asymptote, this is an asymptote, you know, and there's only essentially only a few ways to do this. If you have a branch in between two asymptotes, you either have a U or you have a U upside down, or you have some kind of S curve. And that's why the signs tells you if we had positive and positive, we would have a U. If we have negative and negative, we would have a U upside down. If we have, as in this case, positive and negative, we have this kind of S. If it was negative and positive, we would have the other kind of S. Yeah. So practice this with as little information as you can gather. And that is part of the point. Use little information, relevant, yet as little information as we can gather to draw a good sketch. Example 8. Say we put the x minus 3 on top this time. F of x equals x minus 3 on top, and then x minus 1 on the bottom, and x minus 2 also on the bottom. So the vertical asymptotes are going to be 1 and 2. X equals 1, x equals 2. The horizontal asymptote is going to be y equals 0. Why? Because the bottom is heavy compared to the top, 2x's versus 1x. I know you're going to say, well, are you going to do examples where that is not the case? Yes, although that's going to take a while, but yes. That's the basic information other than the chart of signs. So we got vertical asymptotes at 1 and 2. 1, 2. The x-intercept happens at 3. And the graph is going to be positive. Again, why? Because if you plug a large number, such as 10, we got 7 over 9 and 8, that's 72 on the denominator, 7 on the numerator. So we end up with a positive number. And then if we have single factors, we alternate negative, positive, negative, starting from the right. Okay. And then let's draw the picture. Y equals 0 is the asymptote. Radical asymptotes 1 and 2. X-intercept here at 3. I'm not going to draw it yet. Now the graph goes from positive to negative. So between 2 and 3, the graph is negative, which means the only way it can go is this way. Cross the x-axis because we do cross it at 3, 0. And then instead of going up like that, go up a little bit to show that we actually crossed. But then we have to go towards the asymptote, the horizontal asymptote. So we have to curve and then S it a little bit so it actually has a soft landing towards the y equals 0 line. There. So this is 3. Between 1 and 2, the graph is positive, 1 and 2. So we have a U. And we don't touch the x-axis because there's no x-intercept. To the left of 1, the graph is negative. And voila, there we have it. Well, the only thing missing is the y-intercept. So let's find f of 0, which will be 0 minus 3, negative 3. 0 minus 1, negative 1. 0 minus 2, negative 2. So we have negative 3 halves. So this point where the y crosses the graph or the graph crosses the y-axis is 0, negative 3 halves. And that's a good sketch of the graph. 9. See, there's a lot of cases. Yeah, let's do, and unfortunately, I cannot give you all the cases because there are too many, way too many. And we have to think of the principles. It does help to read books that have a section about rational functions, but we cannot, the number of total examples is too large. Let me give you an analogy, a quick analogy about that. In elementary school, at some point, we learn how to add whole numbers, 3-digit numbers. So this is an analogy of what I want to say. Let's say we're learning how to add 3-digit numbers, such as, I don't know, 752 plus 695. At some point in your school career, in elementary school, you learn how to do this. How many such examples are there of 3-digit numbers? Well, there's about 900 of those, okay? Because the 3-digit numbers start with 100, and then they go all the way up to 999. So there's 900 of them. And for the second number, there's 900 of them. So if we multiply those out to have all the possibilities, we end up with 9 times 9, 81, and 4 zeros. So how many possible additions of 3-digit numbers are there with another 3-digit number? More than 750,000 examples. There's more than 750,000 examples. And somebody could say, well, if you have 1 and then you do the flip the other way, that should count as the same. Fine. Even if we divide this by 2, we end up with close to 500,000, for sure more than 1/3 examples. Nobody wants to show you 1/3 examples. And you wouldn't want to see, even if somebody wanted to show you 1/3 of a million examples, nobody would want to see 1/3 of a million examples of the same kind of problem. You know, how many examples do they show you when they're teaching you this? Maybe 4, 5. That's it. And then you're on your own, you know, and then that doesn't cover every single thing that could happen. I mean, we could carry a 1 here, or we can carry a 1 here, or we can carry 1 there, or we can carry 1. You know, there's many things that could happen. Or what if we have a 0 there or a 0 there? You know, there's many different things that could happen. Mind, yeah, I know this is a simple example, but even this simple example has many, many possibilities. Well, when you have rational functions, the number is even bigger because there's too many things that could be different. You can have 2 factors on the numerator and 3 factors in the denominator, or you can have 1 factor in the denominator and 2 factors in the numerator. In fact, that's what I'm going to do next. There are many, many possibilities we can have. No teacher wants to show you all of them because there are just too many. I mean, if there were like 1/3 of a million here, I don't know, there's many here. And no teacher and no student wants to see all of them either. So we have to go by the basic principles. Okay, so say f of x equals, let's put x minus 1 and x minus 2 on the numerator and x minus 3 in the denominator. Now that changes the situation completely. Okay, this is top heavy. The degree of the numerator is 2, the degree of the denominator is 1. So we don't have a horizontal asymptote. We have, in this case, a slant asymptote because the degree is bigger than the degree of the numerator is bigger than the degree of the denominator by 1, 2 and 1. Okay, so no horizontal, I misspelled that, horizontal asymptote. So we have to remember, when do we have horizontal asymptote? When the degree is the same on numerator and denominator, or when the function is bottom heavy. So no horizontal asymptote. We do have an oblique asymptote because the numerator has degree 2, the denominator has degree 1. This is complicated. It is, but it is a good thing. We want to be able to handle complicated issues, such as this one. The beauty of math is that it's very easy to get to complicated issues. It's very quick. And the other beauty about studying mathematics is that we can get to complicated issues without much opinions. The opinions in mathematics are very few. Are there opinions? Yes, but there are very few. We can get to complicated issues without controversy. Yeah, with very, very little controversy. The only controversy that I typically hear is students saying, oh, this is too hard. You know, why should we do that? And I can give you a good reason, because this is a very efficient way to get to a complicated issue without controversy. And that's a good thing. Anyway, oblique asymptote. So multiply this out because we're going to do long division. If you thought long division is behind us, no, we have to do long division. So multiply that out. We're going to end up with x squared minus 3x plus 2. We're going to divide by x minus 3. Oh, well, if we divide by x minus 3, we can use synthetic division. 1, negative 3, 2, and we're going to put 3 in front. So bring down the 1. 1 times 3 is 3, 0. 0 times 3 is 3. No, 0 rather. Add that together, we get 2. Never mind the remainder. This is x. So the quotient is just x. The remainder, let's write it down, is 2. This represents the x. Had this been 5, just to give you an example, it would be x plus 5. Okay, this is the horizontal, whatever the quotient is, that is the y equals that quotient is the horizontal, the slant asymptote. This is the slant asymptote. So when we ask you what is the slant asymptote, multiply out, divide the quotient, y equals the quotient, that's going to be your asymptote, your slant or oblique asymptote. Okay. So we have that, and we have one vertical asymptote, x equals 3, vertical asymptote, x equals 3, and we have x-intercepts 1 and 2. Okay, so let's do a chart of signs. Let's draw a chart of signs. Okay, so 3, we have a vertical asymptote. We got 1 and 2 as x-intercepts. Yep. We start with positive. If we have single factors, 1, 2, 3 single factors, we simply alternate from positive to negative to positive to negative. That's 2, that's 1. And we can start drawing our picture. So we have an oblique asymptote, y equals x. That's a dotted line, not firm line. Yep. So we have a vertical asymptote at 3, x equals 3. This picture is already messed up because this line should be farther to, this point is 0, 0, 0, where they cross. And I have to squeeze 1 and 2 between 0 and 3. This is 0, this is 3, and I want to squeeze 1 and 2. And in my picture, I don't have enough room, so I have to separate this. I'm going to draw a new picture to do that. Now that I know, okay, so there's the oblique asymptote, there's the x-axis. Boy, this is not going to be easy. So there is x equals 3. Yep. And the function is going to be positive on the right of the 3. And the only way to get a function that is positive following those two asymptotes is by doing this. Okay. Between 0 and 3, we got two x-intercepts, 1 and 2. I'm not going to draw them yet because I want to draw the picture, a picture that is smooth. So the graph is negative. Why? Because we alternate signs from positive to negative through the 3. Negative means under the x-axis, so we're going to do this. But then we got to go through the 1, and then we got to follow the other asymptote. Yeah, this is not super easy. So this guy is 1, 0. This one is 2, 0. Vertical asymptote, oblique asymptote, y equals x. And that's about it. Oh no, we're missing the y-intercept. Oh, but the y-intercept, I was going to say 0, 0, but it isn't. It is somewhere here. I typically don't draw the y-axis because I don't want the y-axis to get on the way of the scaling of the picture. But let's find out what it is. F of 0. Now I forgot what the formula was. There it is. It is 0 minus 1, 0 minus 2 over 0 minus 3. And that's going to give us 2 over negative 3, or negative 2/3. So the y-intercept will be here somewhere. Negative 2, whoops, 0. No, I forgot what it was. 0 for the input, negative 2/3 for the output. I guess we can do this. 0, negative 2/3. There we go. Yeah. Yep. Let's do an example with a horizontal asymptote, which is not 0. example, is it example 9? No, we did example 9. Example 10. Say we have f of x equals 7 quantity x minus 2 times x minus 4 over 5 x minus 3 times x minus, I want to be past the 4. I don't want to use 5 again. Let's do 6. There we go. I don't want to repeat numbers so that we don't get confused. Okay. Vertical asymptotes, 2 and 6. Rather, 3 and 6. Vertical asymptotes, x equals 3, x equals 6. X-intercepts 2 and 4. I didn't write them before, but let's write them. X-intercepts 2, 0, and 4, 0, coming from those two. Horizontal asymptote, that's an A. Horizontal asymptote. Okay, what is the degree of the numerator? 2. The degree of the denominator? 2. So this is evenly, this is balanced. Numerator and denominator are of the same degree. So we look at the leading coefficients. Technically speaking, we're supposed to multiply this out. You know, we're going to end up with x squared minus 6x plus 8 times 7. But the important thing is the x squared times the 7. So we're going to end up with 7x squared plus other stuff of lesser degree. On the denominator, we're going to have, similarly, 5x squared plus other stuff of lesser degree. What is important is the 5 and the 7. The horizontal asymptote will be y equals 7 over 5. We just keep it the same way. And then we do our chart of sines. 2, well, 2 is an x-intercept. Then we got 3, a vertical asymptote, 2, 3. And then we got another x-intercept, 4, after that. And then another vertical asymptote, 6. Okay. There's no negative x's or negative in front of the ratio or negative in front of the 7 or the 5. So that means that if x takes a big value such as 10, we end up with 7 times 8 times 6, because I'm assuming x is 10, 5 times 7 times 4. All the numbers involved are positive, so the whole thing is going to be positive. If we have single factors, we alternate from positive to negative to positive to negative to positive, and then we start drawing our picture. Okay, we got the x-axis. We got a horizontal asymptote, not y equals 0. So this is y equals 7/5. 7/5. We got a vertical asymptote at 3. X equals 3. Another vertical asymptote at 6. I suggest not to put the x-intercepts yet, because you want your graph to be smooth. Past the 6, we have to be positive, and there's only one way to do that. Between 3 and 6, between 3 and 6, we got an x-intercept of 4. Okay, and the graph has to be negative on the right of the 4 and positive on the right of the 3. So we do this. So this is 4, and then we continue down here. So this point is 4, 0. let me pause for a moment to say that students frequently tell me, wait a minute, I thought we were never supposed to cross an asymptote. And that is not true. Uh, this branch does not cross it, but that doesn't mean that we don't cross it previous to that branch. So whoever said that we're never supposed to cross an asymptote, um, I don't know, that's misleading. We can get closer. Yeah, we can cross it. That does not violate the idea of having an asymptote. Um, yeah. I think the emphasis on getting closer and closer to it without touching it, which does happen in many cases, is what leads to a myth that we can never cross an asymptote. That is a myth. In this case, we do get closer and closer without touching it, but in this other branch of the same function, we're crossing it, and there's no harm done. There's no problem. So it isn't. It is a myth that we never, ever, ever cross an asymptote. That is a myth. Uh, as in this case, we do. In fact, we could be right on top of the asymptote all the time. But anyway, um, and then on the left, so this is positive, negative, positive, negative, positive. So the only way to be negative to the left of the 3 with a vertical asymptote at 3 is to go this way. And then we got to cross the x-axis at 2. See, this is why, because I want this line to be smooth, I draw it first, and then once I see where it crosses, that's what I'm going to label as 2. But then we got to follow this asymptote. So we get closer and closer without touching it in this case, but here we do cross it. We do cross the asymptote there. We don't cross it here. So it depends. Sometimes we do, sometimes we don't cross the asymptote. It varies. We cannot just absolutely say we never do. That's the one thing I don't want to say. That's not true. There, that is a sketch, a branch this way, sort of like an L. It's not an L, but sort of like an L, an S curve, another L the other way. So sort of like a quarter of a circle. It's not a quarter of a circle, but sort of a quarter of a circle, another quarter of a circle, an S. The only thing that is missing is the y-intercept. So there's going to be a point here. And the way to find the y-intercept is to plug in 0. I'm going to try to squeeze it here. F of 0 is going to be 7 times negative 2 times negative 4 over 5 times negative 7 times negative 4. No, negative 6 rather. Okay. And then we can simplify. What can we simplify? 7. Oh, 7. So those 7s cancel off. Well, first of all, negative, 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 negative. The whole thing is positive. And then the 7s simplify. What else? A 2 simplifies with a 6, and we have still a 3. And then we end up with 4 over 15. 4 over 15. Yep. So this y-intercept will be 0, comma 4 over 15. Can we do more examples? Yes. This topic of rational functions is extremely rich. There's many, many, many variations. Stick to the vertical asymptotes, horizontal asymptotes, if any, x-intercepts, chart of sines, and a sketch. But use the least information That's maybe what is a little confusing, because it looks like we're doing a lot of things with very little information. Yes, we are, but we are doing that on purpose. We don't want to dwell too much um, on how those graphs look like. By the way, the sketches we make are very, very good in the sense that they give us tons of information in one picture. Can we graph these functions using a graphing calculator? Absolutely. But the problem with the graphing calculator is if you try to get some detail here, this branch may be too far off and we won't be able to see it well. If we include this branch, then maybe we won't be able to see this. When you have a good picture, we have to compromise. Either you get one part really well and the other part is neglected, or vice versa. The sketch doesn't neglect anybody. It keeps everything, you know. I don't want to add more detail to this because there's not much detail to add to it. It's asymptotic in this way and asymptotic that way. Here, there's the important part of this. We got an S curve between 3 and 6 through the 4. What else is there to say? I mean, yeah, you can get down to, okay, what value corresponds to each input. Yeah, sure, we can go past that, but we just want to have a sketch, a general idea of what to expect. This is super duper important because if you have a graphing calculator and you have this knowledge, okay, you know what you're looking for. You're looking for 3 branches, one that looks like that, one that looks like that, and the S. And so if your window is not good, you can change your window depending on what you're looking for. Are you looking for this branch or this branch or this branch? And then you can focus on one of those. Yeah, and sometimes the calculator doesn't give a very good picture of the asymptote. Sometimes pieces are missing on the calculator, and it is not the fault of the calculator. It can only give so many pixels. It can draw only so many pixels. And we're not going to spend a lot of time on technology necessarily that can do a better picture, because even with a good picture with more pixels, we're not going to know exactly what's going on until we have an overall picture of the graph. And this is what we are doing. We want to have an overall picture of the graph. Um, Sometimes I use the analogy of accounting. If I'm a general accountant for a big store and the owner comes and says, well, how are we doing? The store owner doesn't want to know, oh, yeah, we sold a pencil the other day. We sold, you know, uh, 2 gallons of milk. We sold orange juice. The owner doesn't want to know the little itty bitty details of that's not what she or he means when they ask, hey, how are we doing? They want to know, okay, we sold, I don't know, $250,000, and our inventory is such and such. The big picture, what's going on, and we got, I don't know, 50 employees, and just the big picture. We don't want to have too many details, and that's kind of what's going on here. We don't want to have every single point with every single detail. No. We just want to have a general idea of what's going on. As through the x-axis, asymptotes, horizontal asymptote, basic, big picture. Yes, do examples, practice. If you have some kind of, spend a little bit of time. Having said that, we are not using graphing calculators. Spend a little time zooming in, zooming out in using perhaps some technology if you are able to. Read books that have this section, perhaps look at other videos of other people, share them with us to say, hey, this video, I found this video and it is way better than Mr. Saldivar's video. By all means, share it with everybody. The point is that we want to learn. And with this, we will close this video.